Okay, cool. So hello everyone. I'm really glad to be here. Today we're gonna talk about to num some JSON with Rust. So in other words, we're gonna talk about parsers and more precisely about parser combinators. So as Jordan mentioned, my name is Jules. I'm a software engineer at Specify. And without further ado, let's just jump right into the presentation. Oh. Okay, cool. So for a bit of context, why did I ended up writing a parser? So at my current position at Specify, we're building basically some tools to ease the process like between developers and designers. And one of the tools we develop is what we call like the SDTF, which stands for Specify Design Token Format, which is basically like a big JSON file where we store your design token. And if you don't know what like a design token is, it's basically like the smallest unit in your design, meaning like colors, font name, font size, dimensions, all that stuff. Here's like a quick example with like a color. We basically have like a name, a type, some values like red, green, blue. And so this file format is basically some internal stuff so far. And like one weekend, I've just been thinking about like how can we make so that users as well can use that file format, like to leverage it. And one of my answers was basically like, I would like to have an LSP. If I open like that file in my IDE, just tell me that basically like the blue is like 1000 and that's just like not valid for RGB.
Oh, sorry, that happens if you get too close to the projector.
Okay, got it. Basically like, 1000 for blue is just not valid. So basically, okay, let's build an LSP, and I basically like span informations, meaning like line and columns number. So let's just have a look to what I have under my hand. And so as any like Rust developer, if I think about JSON, I'm basically thinking about like Surday and Surday JSON. And it happens that just like not possible, like to retrieve like line and columns information with Surday. So the other options that have like either like looks for other libraries or other like approach of building it, or either make it by myself. And as every developer just ended up like making it by myself. So let's jump into like the subject. What is actually a parser? According to Wikipedia, like a parser is like a software component that takes input as data, often text, and builds a data structure, giving a structural representation of the input while checking for the correct syntax. Well, definitely like a valid definition of a parser. But I think, like in my opinion, it could be a bit more precise to really like emphasize on some really important components of a parser, and that's how I came up with my definition being like a program that accepts non-structured and unusable input as is, creating a data structure that will allow to work with it while validating that this input is correct. That's kind of the same thing, but I really want to emphasize this idea that we have on our hand, under our hand, like something that really we can't use it. Like the most basic example is like everyone like is a developer, and we're basically like our job is making some huge text files, like a big string, and we can't use strings to make like programs. Like there's like this black box that will basically take that string and make it so that you can execute it on your computer, and that's the whole job of like the parser and the compiler. And like generally speaking, when you talk about parsers, we basically talk about like taking like strings or bytes as an input, although like that's basically the same thing. And as output is like the parse tree or the abstract syntax tree. So if you already work with like macro in Rust and other programming languages, that's what you're actually working with. And so to give you like a quick example of what I'm expecting from a parser, basically here's like a quick like simple DSL, if I can call it so, with like just a number, float int, and like an operation. And here is my parser function, and basically this is the idea that this parse function, I'm expecting it, like if I give you something that is valid, well, please like just convert it to me to something I can understand. And if that was too close. And if it's not valid, just please give me some like error to say me like, oh, actually in my case, like hello, it's not a number. That's simple, right? And something that is required when you're actually parsing stuff is basically like defining some rules. Just saying, okay, what is allowed, what is not allowed to parse, and that's actually what we call grammar. So the same way that we humans, when we're building our sentences, we're using grammar, we literally have the same things like in programming languages when you're doing some parsers. And so here's like an example of like a grammar, like really simple, like to build like additions. So defining some white space, like a plus, an integer, then like what is number, and finally addition, so like a sum. And so basically, like the syntax, it looks a bit like some regex stuff. So having like the vertical line being like an OR, then we have like this little wave. Always don't know like the name of this operator. This is like the concatenation operator, and then we have like the little star and plus, which is literally the same thing on regex. So either like 0 or more occurrences, or either like 1 or more. And finally, the question mark being like the optional operator. And so meaning that if you have looked at the addition, it's like I'm allowing like white spaces, then number, then white spaces, then plus white spaces, number, white spaces. And so the important thing about this is basically that when you're defining your grammar, you really have to define like everything. If you want to have some space, like to allow them, you explicitly have to do so. So now that we're a bit aware about like what is like a parser, let's just dive into a bit like the theory of parser and like the different types. So when we're talking about parsers, we actually talk about like two categories, which are top-down parsers and bottom-up parsers. Among them, we can just call like the recursive descent parser, non-recursive descent parser, and also like the LRK and operator precedence, just some complicated names basically. And so the most important thing is actually like the difference between like the top-down and bottom-up parsers. Like, is it just reading like a file from the top to the bottom and the bottom to like the top of it? This is actually what I thought when I first found out about like those words, but that's actually a bit different. So here's like an example of like a parse tree like over there. This is actually what I mentioned like earlier. This is what you're trying to achieve when you're parsing. So we have like right here like the thing we're trying to parse, which is like A equal B plus C times 2 and D equal 1. And like right there you have like the tokens name, basically like the whole thing is like a statements, and then you have some var, like sums, products. That's basically it. And the difference between bottom-up and top-down is like the parsing order. So basically in the case of bottom-up, we're starting from like the smallest piece, like right there, like this one. And then okay, we start from the A, then saying like the A is like a var, and just then next like is the equal. And on the top-down side, we're basically like deciding that we're starting like from the top, so identifying that everything is like a statements, and then we're just trying like to break these statements down into like variable, assignment, and all of that tokens. So let's just run through like some basic examples. So one of the most common like top-down parser is called like LLK. LLK, so L stands for left to right, saying that we're going to parse the input from left to right. The second L is for leftmost derivation. Basically, here in that case, we have our expression, right? And so in the case of a leftmost derivation, well, we're first going to try like to derivate the left number, leftmost derivation. And finally, there's like the K, which is like the number of look ahead you need in order to implement your parser. So maybe like in that case, let's say if you want to implement your parser, maybe you need like to have a look ahead on number plus a number in order to implement it. That would be like an LL3. Then you can have like a 1, 2, 3, like as much as you need. And so here would be like a parse tree, like simple parse tree for this parser, like really simple. We have an expression, some number plus number, simple, right? So now, if I want to make it a bit more complex, I want basically like some kind of infinite like sum. Like let's say I either like having 1 plus 1, I want to have 1 plus 1 plus 1 plus 1 as much as I want. And so to do so, we can do some basic recursion. And the thing is, this is actually, we are going to have a problem with this approach. And so does actually anyone here have an idea of what will happen?
Because you've got number and expression as both as expression, and you're using something that's not necessarily a peg parser, you might get stuck in the expression loop and never actually break down the structure.
Yes, basically that's the answer. So if I show like the parse tree of it, that's something that looks like this. That's the idea that because we're actually like in a like a top-down leftmost derivation parser, it means that we're going to try to parse the expression, right? And then we're going to try to derivate like the leftmost token, which is expression. And so if you want to know what is an expression, then, well, an expression is like right there. And in expression, we need to know what is an expression. And that's basically just some basic like recursion problem. And so That's actually like a problem with like the LLK and top-down parsers, which is you are not allowed to have left recursion. And so a way to actually fix it is basically, well, if you can't have left recursion, what about right recursion? So moving my expression on the right side. And that's actually a fix, like it works. So here I can have my expression, number, plus, and then just another expression I'm breaking down to like number, float, number, flow. And hooray, look, we're happy, it works, until it actually doesn't. So here is like the, well, anyway, here's like literally like the same example, the only difference being like I'm having like a minus instead of a plus. Let's just make like literally like the same example. I'm having like an expression breaking down into like 7 minus 4 minus 3. I'm pretty sure we have some clever people here tonight. 7 minus 4 minus 3, how much is it? You're wrong. And I'm going to prove it to you by basically I'm going to pretend that I'm a computer. I'm going to evaluate everything, right? So I have an expression, 7 minus something. Well, an expression, I need to evaluate it, right? So 4 minus 3, which is 1, and then 7 minus 1, that's actually 6. And so here is like the main problem with top-down and leftmost derivation parser, which is you can't implement valid mathematics because you're breaking like the most fundamental principle of mathematics, which is, well, the left priority, right? And so how can we actually fix it? And the simple answer to that is like is actually going on the opposite, on the second categories, which is bottom-up parser, and most precisely like the LRK parser. So LRK stands for left to right. So same thing, we're parsing our input from the left to the right. The K is still like the number of look ahead we may need to implement our parser. And finally, the R stands for rightmost derivation, which rather than starting on the left side, we're derivating from the right side first. And because we have like this approach, and because of the bottom-up approach, we're basically allowed to parse the 7 minus 4 minus 3 without having any issue. And here is like the breakdown of it to understand like how it works. So because of like the bottom-up approach, which is like having a look to first like the smallest piece, which is in our case like 7 minus, etc., before like having a look to the expression, that's going to work. And so here like we have 7 minus 4 minus 3 again. And so what he's going to do is like 7 minus 4, which is like number minus number. And then the parser is going to look up and say, oh, actually, I have number minus number. That's an expression. And so it's going to do what we call like a reduce and say, oh, that's actually like an expression. And then it just like keep going on. So expression like minus number and then expression minus a number is also an expression, which basically allows us to have like some valid mathematics. And like to sum up quickly, like the main difference between top-down and bottom-up parser is the difference between like a macro and a micro approach, which is on one side, first identifying that the whole pattern is like the expression, and on the other hand, like having first identifying that we have like number plus number, and once we have that in mind, that we can say, oh, that's actually an expression. And this is like a small difference, but that's actually what's allowing us to have like some valid mathematics while parsing. So now that we're a bit aware about like the theory, let's talk about parser implementations. The first way of approaching it is actually through generated parsers. And so yes, there's like a whole libraries that basically are allowing you to just generate parsers. And to do so, you only need like a grammar. So like the same thing I was showing you earlier, which is like super cool because it's like really easy to create, like real fast to do. And then it's also like quite easy to maintain. Like no need to dive into like thousands of lines of code, just update your grammar and just regenerate the parser, and that's basically it. And a good example of it is like the pest library in Rust. That's the grammar I've been showing you like since the beginning is actually like the syntax of the pest library. So each library actually has like its own syntax. Also like everything is like quite similar. But yeah, like that was pest like since the beginning. Then another approach you probably like at least heard about, it's like lexing and parsing. So here we have like this lexing parsing, like you probably heard about it, and this idea that we're gonna break down the parsing into like two steps. The first one being like the lexing and the second the parsing. And so here, if I have my real like basic like string, which is like let hello equal 1 plus 1, the next thing is this step, like I'm gonna take my row input and try to put like an abstraction above it, like which is what we call like tokenization also, and say like my let is actually like a keyword, then the hello identifier, well, etc. etc. Just rather than having like this row string to work with, we can actually have like an abstraction, useful abstraction over it, and then like the parsing, we will define like more like what actually you want to work with, like in the end. In our case, like if you're developing like a programming language, you can say, oh, if I see the pattern like keyword identifier, operator literal, then oh, that's like variable declaration. And that's actually like a quite cool thing like to build parser this way, mainly because like you have like this separation of concerns. So on one hand, like you can really like separate the process of like taking like the raw input like and taking it to like some kind of abstraction, and then like that abstraction into like your final data structure. And another good thing about it is like the performances, mostly because like lexing can generally be done like in one pass, so basically like ON runtime, followed by like the parser that then just can take the advantage of like this abstraction to also like be quite performant. And a thing I think like the better error management as well, mostly because you can separate your error into, well, like the syntax errors, which is like, is there an error in my row string? Like, can I convert it like to tokens? And then more like the logic error, I would say, like the idea that I have like some tokens, but like these tokens, like, do they make sense if they're together? And one final approach I want to talk about is the parser combinators approach, which is like actually like what this presentation is about. So we've talked so far about like the parser, but what is actually these combinators, right? So basically a combinator is like a function that will take multiple parsers as an input and create a new parser from it by composing like this parser. Basically that's like a function taking function as parameters and building a new function from it. That's also what we call like a high order function. But you make like a bunch of functions composing together to create like new functions. Here's like maybe like an example, like to better understand like how it works. Here I'm trying to parse like this 10 like comma like 20, which is like basically like an array like without the brackets, to build like this parse separated number parser. And so I have my parse comma, my parse number parser, and I'm trying to achieve like this, and I'm using like the combinator separated list to say, oh, I have like a list of number separated by comma. And so there's really like this idea that the whole philosophy of parser combinator is about creating some really like small parsers, like simple one, that you will then combine together like to create more complex parser. And in our case, we're going to use like the num library, like the Rust num library. That's why I'm calling this presentation like num, which is like a really cool library, and we're going to see about it like in a minute. And one thing you're maybe wondering is actually like, I'm talking about parser combinators, but like how does it compare to, well, generated parsers and lexing parsing, right? Because like everything has like its pros and cons, so let's just quickly talk about it. So basically if we compare like parser combinator like to generated parser, well, the first thing is that it's code, meaning that in a generated parser, because you're generating some code, it means that the whole stuff, like the generated code, is basically like a black box. You don't have the control in it, and the only thing you're basically dealing with is like the output. Where with the parser combinator, we're going to develop it, meaning that if you want to, in the middle of our parsing, like let's say I have like a plus. In the case of a plus, I want like to fetch like a weather API, although that's quite useless. I can do it. And although like because like generated parsers are generating some codes, it basically means that you have like generated data structures as well, meaning that you'll probably have like this extra step of taking those data structures into your data structures, which is like, again, like something we don't have with parser combinators because we're building like from the start our data structures. And if we compare it like to lexing and parsing, like parser combinator actually like make it into one, like into only like one, like lexing and parsing actually like into like merge together, which means like it's actually like faster to write because you don't have like this separation of concern, just write everything and that's it. And also there's like an easier error management, mostly because when you're doing parser combinators, you do it like through a library, and the library has like a lot of primitives and errors just built in for you. So you can just like use them to build your own like error system. And we're almost done like with the presentation, and before like just diving into the code, I mean. And another thing you may be wondering, like I've talked about like those top-down parsers, like bottom-up. How does it compare? Like how parser combinators generated parser and Lexington parsing, how are they like in the theory, right? And my answer to that would be basically that we don't really care about it. Like you don't need theory. That's the thing, like parsing, like parser looks kind of like a scary task in my opinion, like when you don't know about it. But I could tell you that we're gonna implement like a recursive decent parser, but that's basically not gonna help you implement it, right? So although like theory will help you to maybe implement better parser, you can already implement some quite good parsers without knowing about it. And last thing we actually need, because we're gonna implement some JSON parser, we actually need like a grammar. And so here's like quite a fun fact. Like this is the business card of the JSON creator, and he basically could fit like the whole JSON grammar on his business card, meaning that it's actually like quite small, and JSON is actually like quite a easy language to parse. And with that being said, we can finally dive into the code. Is it like big enough? No. Okay, looks good. Okay, so like first, before even diving into like JSON parsing and all that stuff, I'm gonna walk through like a hello world parser, so everyone can just really like understand like the logic behind parser combinators. And the first thing that we're gonna need actually is like understanding the basic of the basic like of num library, which is like the parser types. And so when you're using parser and the tag, which is like right there, being like the most simple one, we're always gonna get like this I result type out of it. And this I result type is basically like a generic over I, O, and E. I being like the input, O the output, and E like the error type. And so in our case, like the input will actually be always string, like str, which is like right there. Then the output will actually depends on the parser. Maybe we're going to return like a Boolean string. That will depends. And the error just like, well, num's error management. And so one of the most basic like parser being like the tag parser, which basically say, oh, I want you like to find the hello string in this hello world. And if I just go through the executions of package step 0, cargo run, that's basically returning here like a OK with like a tuple of space word and hello. And so the way it works is by this parser, when it's succeeding, it will basically return you two things. The first one being what he could parse, and in our case, like here, because we're asking him like to parse hello, he could parse like hello right there. And the first element of it is like the rest of our input. So in our case, because we could parse like this hello here, we are still with like the space word, which is like the untouched part, like the part that we still have to process to continue like the parsing. And so now that we have that, let me comment out everything and uncomment the rest. Cool, that looks good. I just have to import stuff again. And you're right there as well. Okay, cool. So when I talk about like the kind of fancy hello world parser, my whole point was basically we have like those hello world strings, and I want to be able like to parse those strings like even if there's like some capital or no, like the basically case insensitive. Then if there's like one space or like multiple spaces, right? Is also like line breaks. And finally, I want to have like this little like is happy mechanism, which is basically like if there's like an exclamation mark at the end, I'll say like the user is happy, and everything. My goal would be like to parse everything to that hello world data structure by retrieving like the hello string, the world string, and finally the is happy Boolean. So let's get started. Well, if you remember just the philosophy of parser combinators, just start with like really small parsers and then combine them to create like more complex parsers. And that's actually what we're going to do. So first, let's just start with the hello parser, which is going to return like a string. Okay, cool. And let's just get into the implementation. So we're trying to parse hello in our case. And so down there, we just need like the tag parser. And that's basically what we need, but we just need like the case insensitive version. And that's actually what is like this tag no case. And then we just tell them I want to parse like a hello. And that's basically it. Then the thing is like we actually need like, because like this parser is returning like a function that you need to execute with like the input in order to get like the output of it. I'm just going to pass here like the input, and we're almost there. Like if you have a look, oh, we can't see it, right? Maybe if I show down there, people in the background won't be able to see. Well, anyway, basically like this parser is returning like a string, like the slice string, and not like a string allocated one. So we actually need to convert it. And so to do so, we can basically then like just do it like the rest way. Like we're just getting like a result out of it. So let's just like ignore the result like with like the question mark operator. And if I can, it's really like, I'm used to my dark theme, and like with the white one, I actually can't see like my cursor. Anyway, so we get out of it like the inputs, like the rest of our input, and then like the hello that we could parse. And then I just have like to return like an OK, the rest of our input, and then our hello, and say I'm gonna to own to make it into a string, and that's it. We have our hello parser. Now I can basically like duplicate that function into like Word, and here Word as well, Word to here and here. That's it for the word parser. We're almost like half the way. The next thing that we're gonna need is the is the happy parser. So basically, is there an exclamation mark at the end or not? Okay, cool. And is happy. And then in our case, we're not going to return like a string. We're going to return like a Boolean out of it. Okay, cool. So how do we do it? Like I can actually like use it like the same way before, like this tag no case with like an exclamation mark in it. Although like a case insensitive like exclamation mark is well quite useless. So I could use like the not case insensitive, like a case sensitive version. But there's still like another option being like I actually need like one char. So I can literally use like the char parser, saying like I want to parse like an exclamation mark, and maybe that's better. And because like it's optional, actually I need to make it like optional, and the way I'm doing it, I'm going to use like a combinator to do it, which is literally like the OPT combinator. And I just need like to import everything, I guess. Yes, char 2. Hello, sir. Let's just, I guess, import by myself, tag no case and char. Okay, he doesn't want to do it anyway. Okay, now he wants. Anyway, okay, cool. We have our OPT char, but the thing is, like, because we're marking like an OPT char, like that's gonna return like an option of a char, which is still not a Boolean. So we could like do like the same strategy that we did before, which is like just extract it. But I'm gonna show you like another way of doing it, which is like through the map combinator, which is literally the same thing like option.map or option like result.map, where we basically like take the result of our parser that is on the left side, and we get out of it the result of it, and I curse like an option, and we can basically just say like option like is it sum, and execute everything. And that's basically it. And also, yeah, I need to implement like the map to import it. Okay, cool. We have our is happy parser. And the last thing that we don't have to forget about is actually right there. Like this is like actually the spaces. We need to be able like to parse it as well. So white spaces, and we're not returning like a Boolean. We'll be returning in that case. That's actually like slice on a string, and okay, cool. And so, okay, in that case, we're not parsing like a single char or like a predefined string anymore. We're actually returning like we need like to be like as long as they're white spaces or line breaks, we need like to be able like to retrieve them. So we basically need like a loop to do so. And so there's like a bunch of loop that comes with num. And in our case, like there's like here, like take till, like take until, take while. And in our case, we're be using like the take while, which is literally like a loop with like a condition saying that as long as it's true, then you just keep getting like the thing that we're matching. Pretty like simple. So we're retrieving like here like the arguments, we're retrieving like the char we're currently like matching. And so I can basically just say if my char is like a space or it's my char is a line break, well, we can just like keep getting chars, right? And I just need like to pass my input. And that's it. We have like the white space parser, just stating as long as you can find spaces or line breaks, just keep getting like just keep accumulating strings and chars. Sorry. Okay, cool. Now we have like all our basics components. We just need like to combine them together to start creating some more complex parsers. And the first one I'm gonna do is the hello world parser. And I'm actually gonna duplicate that. Yeah. By the way, ignoring like the like the error part, mostly because we're going to talk about it later, about like the whole generic stuff. So just ignore it for now. We're going to talk about it later. And that I'm going to create like the hello world parser. And so if we want to create the hello world parser, we basically need like to combine the hello word and is happy parser, right? So that's what we're going to do. And we just basically need about what is actually our hello world. If we just look down there, like the hello world is literally like a pair of hello and world separated by a bunch of spaces, right? And that's not that complicated. So we're going to use literally like the separated pair parser. And it literally takes like some parser as argument. The first one being, well, the hello. The second one being like the white spaces. And the second one will be the word parser. And we can just execute it, and we already have like the strings that we want to return. Oh, and I'm just forgetting about the return time here. What we want to return in that case, like the string, and a bool. So basically like a tuple with hello, word, and the is happy. And then I can get out of it like the next input, and then a tuple with like the hello and the word, mostly because like the separated pair is actually like well built, I guess, thing that we actually care about like the hello and the word. We don't really care about like the separator between it, so it's only retrieving the hello and the word data. Then we just have to apply like the is happy parser on the next input, which is like this one, and then we can just retrieve like again next input and is happy. Cool. And again, we're just like ignoring the error. And finally, we can just return like an OK with like the next input and then a tuple with hello, word, and is happy. And if we do so, we actually have our hello world parser, and we're almost done. Now we can finally implement this parse function, because although we're parsing hello world, it actually lacks just two things, which is this white space is before hello world and at the end of hello world. So we also need like that thing, which is the hello world is actually delimited by spaces like at the beginning and at the end. And that's literally like what we can use, the delimited combinator, where we're going to say like we first have white spaces, then we have our hello world, and I can actually get rid of that, I guess. And here we again have some white spaces, and we're almost done because now we're actually retrieving like the tuple that we created just before. And so the last thing we can do is again using like this map combinator to just map on the output of our delimited parser, which is going to be the hello word, and finally the is happy. And I need to delete this unit. And then we can just make it into our hello world struct, passing like the hello word and is happy. And here passing everything, and oh, okay, everything has to be wrapped into a tuple, and that's happy now. And that's basically it. We created our hello world parser, and so we now just have to execute it. And if I do so, you can see that we have here our OK with like an empty string, meaning that we went through our entire input. We parsed everything, nothing is left. And then we created our hello world structure with like the hello word and if it's happy or not. And finally, if there's some errors, because here we have like this not, which is between the hello and word. So there's an error, and same thing here. We have our hello with like only one L, so that's an error. And that's basically that simple to create some parser, just a bunch of simple functions we combining together, and that's basically it. So now let's dive into a bit more some real-world use cases with some JSON. So let me switch to main here, right? Okay, cool, and oh. I need to uncomment that and then comment that. Okay, cool. So the code I'm going to show you right now is actually not my code. That's the code that we can find on num GitHub repository in their example folder, which is like the JSON example. And that's actually like a really good educational example, but in my opinion, like terrible production code. And we're going to see why in a minute. So the whole purpose of this code is actually building something that is quite similar to sorted JSON, which is basically like this enum with like an object, like a hash map, basically like a vector, and Boolean string, null, num, well, JSON, right? And to do so, it's literally like the same thing that we did before, just some simple parsers we're combining together to create more complex parsers. So here, if we have a look, we have like the Boolean parser, which is literally like, well, if we find true, then that's true. If we find false, that's false, and that's basically it. Null is like, if we have null, then that's like a unit. And then in the case of a string, it's a bit more complex, but basically it's like, here we're saying like our string is preceded by, oh, I went you down, oh, right there. Cool. Our string is preceded by like a quote, and it's terminated by a quote, which is literally the same thing that's saying like our string is delimited by quotes. That's just like you can actually achieve it like through various way. And then we're using like this parseString function. And so this parseString function is actually focusing on like the content of the string and is using like a pre-built escaped parser, which is basically here to help us to handle all the escape and control char, right? Because if you're having like only like double quotes, how can I have a quote inside my double quotes? And that's through escaping, and escaping is actually a thing you have to handle by yourself, which is something like num is providing you. So super cool, we don't have to go through it. But yeah, that's the kind of thing you have to handle. Then we have like the array, and if you have a look, basically like there's a lot of syntax around there, like this context, like the cut, everything is like error related. We're gonna talk about it later. But basically, again, it's literally like preceded, saying that it starts with like a bracket, it ends with like a bracket, and then here we have like a separated list 0 of JSON value, and the separator is like a comma. And this idea of like separated list 0 is saying that we can actually have, well, 0 or more elements because we have to handle like the empty array case. And we're gonna have like the same thing right here in like the hash function, which is like the object. Here we have like the separated list, but like rather than having like JSON value, we're actually like handling like key value, because like in that case we have to handle that first. We're trying to parse like a pair of, well, a string, then like colon, and then another JSON value. And finally, if we have a look to this like JSON value, it's actually basically a parser saying that I'm gonna like with this al parser being like the important thing. That probably stands for alternative, I guess, which is basically I'm going to try to match your input against all the parsers until it works. So that's basically just a loop, and first it's going to try like, is it like a hash map? Oh no, then is it an array? Is it a string? Is it a Boolean? Is it null? Is it a double? And that's basically like the way it works. And just trying to match like your input. And then now finally, if we try to match like that code, so read like some basic JSON, so well, a like a number, an array, object, and although like even if we have like like some spaces before, we have like some line breaks here. And if we just try to run the parser, step 1, then run, we're saying we can see that we can on one hand, like on one side, like achieve like to parse into like an object that have like a number, then an array. So cool, it works. And on the other hand, like here we can see like if I show you maybe like this input, there's like here like a little one before like the hello, which is like not valid syntax for JSON, and it just like achieved to tell us that I actually fail to parse like at that point. And that's basically like the basic like of a JSON parser. That's not like that complicated. It's like literally if I go, it's like 140 like lines of code. That's actually quite small. But now I just want to show you like some quite interesting thing and why I actually told you earlier that's definitely not some production-ready code. By actually using like this parser against like this Canada.json, which is basically like a 3 megabytes JSON file that contains all the like the geopoints of Canada. So you can imagine just like all the geopoints of like the border of Canada, just like to see how it can perform. And so again, if I just run it, it's taking like something like 600 milliseconds, which is, well, not that bad, I would say. Like, I mean, under a second, why not? But the thing is, we're parsing like 3 megabytes in 600 milliseconds, meaning that we're basically parsing like 4, 5 megabytes in a second, which is actually quite bad. It's not like that great. And the main reason behind it is actually like the JSON value parser, because I told you that the way it's working because of this alternative parser, we're actually trying to match our input against our parser until it works, meaning that if we have like 1,000 values, well, in the worst case scenario, we're gonna match it against like hash, array, string, boolean, null, and double until like we find like the one who is working. And this is basically what we call like backtracking approach, which if you do it that way, you're basically ending up like your parser being like with like an exponential runtime, which is basically like just terrible. And so let's see how we can fix it. So like the only thing we have to do in order to just improve the performances is like change a bit like the way we're approaching this JSON value parser. And so the way we're doing it, rather than like just trying like to brute force our parser, we're gonna do it like a bit more like cleverly by just saying I'm gonna look my next char. And because of the grammar of JSON, like it's actually super easy to do it, because depending on the first char, you can basically infer what you're supposed to do. Because if you have like the curly bracket, then that's an object. If you have like the bracket, then that's an array. If you have a quote, that's a string, a minus, or like a number, well, that's a number. If you have f, that's false, t, true, and null, and that's basically it. Like because of the nature of JSON, like it's actually super easy, like just to infer like what we're supposed to parse, and just to improve performance, only with like that little change. Because if I again just let's go to step 2, and run everything, like that's actually like a ×2 improvement over input, which is again like quite okay. But like again like 3 megabytes, 300 like 400, that's basically like 6, 7, 8 like. Something like 8 megabytes a second, which is like still like not that good. And so here we're gonna basically attach to like a quite limitation of that kind of parser, which is like generally speaking, like parser just spends a lot of time like doing allocations, right? Because in that case we're allocating like a bunch of numbers, well strings, on the heap, so that just takes time. And so allocation is a bit slow when you're doing it like at debug time. But if we're actually doing it at release time, where like we don't need like all the debug informations, we can actually like take down that time to like 44 milliseconds, which then in that case, like it's, well, let's say like a 10 times improvement. So we are basically taking like to 8 megabytes a second, like to 80 megabytes a second, which starts to be like quite, well, reasonable for a parser, in my opinion. But now there's like, it's still like not production ready, although we have some great performances. And so we still have a thing to handle that is like quite important, because we're right now in Tokyo, right? And I'm expecting you to actually at least know that here people, Japanese people, talk with like hiragana and katakana. There's no such thing like as ABC, right? Well, although Romaji, of course. But what about like if I just put like a A inside my string, right? And just let's have a look, I guess. And oh, did I saved? No, okay. And then okay, package step 2, and cargo run. Cool, and that's actually failing. And the main reason being that our current parser can't handle UTF-8 and UTF-16 chars, which is basically a problem because if you read like the JSON RFC, you're supposed to handle them. Like you don't have the choice. So we will have to handle those chars. Let's go to step step 3. Okay, cool. And so how do we actually handle them? And so to do so, we sadly have to get rid of the pre-built like escaped parser that was like so helpful at the beginning, and basically implement by ourselves a string parsing function. And so the string parser is literally the same thing, but like rather than having like this parse str, now we're having like this parse char function, where basically we're gonna have a look to every char we're trying to parse in our string, and if we find, in our case, like the escape char, which is like the n/, we will have to do some verifications. And so here, in that case, like if I find it, maybe we're gonna like to have a look to the next char to make sure like we're having like n, r, or like an r or t. Basically, like those values here being like the ones allowed by JSON. And in the case of like this little u, it means that we have like some Unicode stuff here. And so I forgot actually to show you, if I go back to the step 2, that's literally this part. So this little u is like the same thing than the a right there. So we're just basically like, this is like the manual way of doing it. We're just saying like, we have like an escape sequence of like Unicode, and then here we are putting what we call like the code point of the char, which is basically like its ID. And that's what we actually have to verify. And if I go back here, okay, cool, and then that's okay here. And the reason we actually have to verify it is because UTF-8 and 16 have some like rules, and they have like some valid and invalid values. And if you want to be like exhaustive, you have to validate that the provided code point, well, is valid. And so that's actually what we're trying to achieve here, saying that if we only find like one of them, then that's like UTF-8, and where UTF-8 is basically like valid between like those values. And if it's like UTF-16, then we're gonna have like two Unicode like following like each other, and we will have like to validate each like the two of them. And those two are actually what we call like low and high surrogates. But yeah, basically like some code points and some like UTF-16 stuff. And again, we're just validating that those values are correct. And once you finally have those values, like those function implemented, well, you can finally, and if I go back to step 3, okay, cool. And now we can finally parse like UTF-8 and UTF-16, and you can finally like start your business in Japan. Now, the last thing I want to talk about, because we finally handle like UTF-8 and UTF-16, we have like some decent performances. The last thing we have to do is error handling, because if people are using your software, cool, but you need to give them some feedbacks, right? So what are they messing up? And so nums comes like a bunch of predefined errors, and that's the reason why we've been using some generics since the beginning of this presentation, because you can dynamically pass some errors, and then it will be like propagated in all your parsers. And so here we're using like this most basic, which is like the error, like the one provided by num. And if I just run this parser and I go to package step 4, and then I can run, like that basically looks like this. So like a simple error, like the input, like where the error happened, and then this code saying like it happened like on the char parser. Okay, cool, but like that's basically like not that precise, right? So let's actually change this error to like a verbose error. And if I just now run my parser, well, it quite changed a lot because we now have like more informations. We have like these, well, errors, actually array, because like it's accumulating all the errors. And we also have like some context in it, like map, telling us like, did it happen at the map level? And so that's actually what I was just telling you to ignore a bit earlier, which is like literally, where is my hash map? Okay, right there, which is like literally like this part. So by adding here like the context combinator, it will basically help us to add some informations when there's like an error happening in order to just like, well, help you like while debugging, basically. And here there's like this cut function, which is quite important because in num there's like actually like two types of error, like the normal error and like the failure errors. So like the normal error is actually like what we call like a recoverable error. So basically it's not like that big of a deal, an error. And that's actually like the way like our alternative parser was working. Like the way it works, like if I have an error, then I'm just gonna skip it. But like if the error is like a failure, it's gonna stop everything because this failure error is like the everything's red, like we have to stop everything, like please stop everything error. And so like this cut parser is basically converting like a normal error to like a failure. Because in our case, we want to say that, well, if I'm in the hash parser, but I don't have like this curly bracket, well then that's actually something where it went wrong, right? Because we're actually verifying right here that we're supposed to have like a curly bracket. And final thing that we can do is, of course, building our own errors, right? And that's what I just did right there, like this JSON error. And just for the simplicity, like building like a num error and like a custom. But of course, like you could put inside like all the missing like the training commas, like if there's like a missing like quote, your own error, basically. And you just have like to implement like a bunch of traits. Basically, like here we have like the error trait. Right there. So we have like also like display trait, and then here we have like the parse error trait, which is like the one required by num, where we're asking you like to have like an input and like the num error and just like do something with it, like convert it to your error, and that's basically it. And also we have like this append function because num is actually, because like when we're failing, like we're gonna have like to go back some layers. If we're, for example, like parsing something deep inside our JSON, we can accumulate errors, so you may give the user like more precise feedbacks. And that's why like there's this append function, although in that case I just did not implement it like for simplicity. And now if I just go back down there, cool. Like because I've implemented all the required traits, I can just replace this by my error value, and that will just work. So I can run again. And I'm gonna have like this custom error, which is like word because it failed like on a chart, and that's basically it. And the last thing I want to mention is that we're actually working with like this E. Like since the beginning, like everything is like a generic, but my personal recommendation would be like to get rid of this error generic, mostly because once you'll be building your own parser, you're gonna be like specific about the error, the kind of error you want to return. And that's a bit like easier to actually work with like the type of your error rather than like with the generic, which will have like a bunch of constraints depending on like the traits you're implementing it or you're actually requiring it to have. So in my opinion, it's just easier to just get rid of like the E generic and just have your own type instead. And with that being said, that's actually the end of the code. So everything is available on GitHub on my repository, like Tokyo Rust Meetup, if you want to have a look. So yeah, I guess maybe we can just share it like another way, but yeah, anyway. So well, thank you everyone. Really like super cool to be able to present. I want to really like to thanks like Mate and George for inviting me. Really cool of them. They really helped me like to review also like all this work. So well, thank you everyone.
Thank you for your presentation. I like how you end at slide 42. To be a little bit more in the center here. Yeah, are there any questions for Jules?
This might sound kind of silly, but you know, when you were explaining how it worked, you were threading the remaining input from one thing to another to another. And then you use map at some point.
Yeah.
And I just couldn't help but think to myself, like, do they have flat map?
That's a good question, and I would say yes, they have flat map. But like I think like for like I think like the best example of it is like if I go back to quickly like to the step 0, here with like the hello world right there. So actually, like, if you're getting into like some map and flat map, like I had this issue of you're trying to pass values between like some closures, and you're getting a bunch of like runtime, and like you basically need to make copy of your string, which basically it's actually like easier like to go through that process. But yes, they have like more combinators, and you can just make like in the end there's like a result, so you can just like use like and then and all of like the result like functions that you want.
Next question.
In the Rust ecosystem, there are several parser combinator libraries that are kind of competing with each other. Have you used any of the others? And if so, which one, or why do you prefer NOM? Or do you prefer another one?
I'm sorry, that's going to be like a quite short answer because it's no. I mostly like, I was just searching for like a parser combinator library, and NOM have been like the first one I found out about. And there was like this, generally speaking, like, great documentation, I would say, like what they call like the nomi-nomi-com, which is like quite well done in my opinion, like a few examples. And just because of that, I just went, it looks like I can do what I achieve what I want to do. So I just went with it. But yeah, I don't have the name in mind, but yeah, I read that there's other parser combinators library, but just didn't have tried them so far.
Thank you.
Well, following up on that, you started out with a discussion about the pest crate.
Yeah.
I was curious if, because it looked like pest in many ways accomplishes the same thing. Like as you know, it compiles the .pest files in a macro, but ultimately you get a state machine parser combinator. So I was curious, how do you feel about the pest versus NOM trade-off, and have you benchmarked them? Like, or is there something about NOM that you prefer over pest?
So when I first started like the whole journey of like when just basically building my own parser, like there was also like this purpose of like just educational purpose, and so I felt like if I went like to some generated parser, like that wouldn't be like the same thing than just building my own parsers. So that's the main reason why I actually went through like NOM and parser combinators. And about like performances, like that's actually what Pest is showing on their website. Like it's supposed to be like a bit slower than NOM, and a bit also slower. Like everything is slower than Serde. But I didn't run any comparison myself, and yeah, maybe because I just wanted to learn about parser combinators. That's why I went with this path. But definitely, I would say that if you're building more like production software, just going through like a generated grammar is probably like way more safe than just building your everything like from scratch. Parser combinator is like super nice. You have some just maybe like prototyping to do, but just having some real like verified stuff, like just like generated parsers, in my opinion, is maybe like probably like better.
Yeah, I mean, it looked like what you got out of Pest. I mean, I only looked at it during your talk, but it looked like what you got out of Pest was a parser combinator, also just expressed using their DSL.
Yeah.
Rather than in native Rust code.
Why did you choose a LL1 parser instead of a PG parser?
That's a good question. Yeah, I guess everything will just come down to I wanted to learn about parser combinators, and so I just have like this NOM in mind. Like I found out about NOM, and in the end, I just like, well, that looks great to use. So there's not really like some really like strong opinion about it. Mostly that I liked NOM and the approach, and I just wanted to learn about, so I ended up just choosing it. So.
Okay, so basically, you can use the same technique to use a recursive decentralized technique to write a peg parser. Mm-hmm. And actually, if you rewrite the grammars to the peg grammar, it should be easier to implement such a parser.
Yeah, I definitely agree. Like if you're just only writing grammar, just like more concise, like just quicker to do, right?
Right.
But yeah, just like in my opinion, because you're generating some code, like you're not learning as much by writing it yourself. But again, like the whole thing was you just have to bear in mind that was mostly for educational purposes, and that's why like writing everything by myself is like the way I just chose. But
okay.
But
maybe the next topic.
Yeah.
Thanks.
Exactly.
If there are more questions from the audience, I'm happy to take them. Otherwise, I'll just ask my questions. Maybe more general about who are you and how did you get into programming?
That's actually like a fun fact. Like when I was in middle school, like we had like this class, like French class, like I'm French, And so during like the French lesson, we went like to the computer room, like to do some online exercises, and I just randomly hit like F11, which happened to open like the Google Chrome debugger, and I just had like like just like a child seeing like a lot of colors, and I just touched like on the CSS like colors, and I saw like I could update like the colors of the website, and I was like 13, I guess, and I just felt like a hacker, and then I reloaded the website, and I was just like really like disappointed. But that's basically how I just get to know like the programming world, and I decided like I want to get it. I just wanted to learn about like that little like things I just randomly found about.
And how did you end up in Rust?
Well, before Rust, I'm still like mostly into web stuff, and when I was like I think like a second-year student, I just wanted to learn more about low-level programming language, because I've been so far like doing mostly like JavaScript, TypeScript, PHP, all of like the web stuff, I would say. And so I'm like, oh, Rust looks cool. Like I've also done like a bit of ReasonML. Anyone like doing just know ReasonML? Two folks, okay. Oh,
It's like
three folks.
OCaml with curly brace syntax.
Yeah, exactly. Well, OCaml, but like the TypeScript, JavaScript flavor, basically. But yeah, like so I was a bit into like functional programming, and like I saw like Rust, like having also like this functional programming like flavor, and like being like low level, and I was like, oh, I'm gonna just go into like more low level code, and that's basically how I went into Rust.
So with that background, what was hardest for you when learning Rust?
Well, because of that background of like the ReasonML, like the functional background, that was like quite easy like to understand like all this like matching like result option, like all the, just to say some buzzword, like all the monadic stuff. That was like quite, I was used to it, but like on the other hand, there was all this like like the lifetime references, things that I was just not used to it. So that's probably like the most difficult thing I've been like seeing so far. Although like I'm finally like getting out of it, but then there's like async Rust, and then that's just like another wall like you have to climb. But yeah, basically I think like all these low level, like the thing that you just basically don't have in the web, were like the maybe like difficulties that I faced.
All right. Maybe last question for any next Rust meetup talk. Which topic would you like to hear?
That's a great question. Another topic. Do I have to answer? I really have nothing that comes to my mind.
Okay, we'll see who's next. If anybody interested, feel free to raise your hand and let us know. I think that's it then. Thank you.
Well, thank you.